Welcome back, all you calculus jocks. Today we're going to look at how we find the radius of convergence for a Taylor series. And what we're talking about here is something that I think has been mentioned before. If we have a Taylor series for some function f of x, we'll write it out. So here we have a Taylor series centered at A for some function f of x. And essentially there are three possibilities. This Taylor series might converge for all real values of x. Or it might converge only at A. That's a pretty extreme case and a pretty boring case. More likely, it will converge on some interval about A. Now that interval might be an open interval, or it might be a closed interval, or it might be, believe it or not, what's sometimes called a clopen interval, closed at one endpoint, open at the other. And we'll be investigating that in this section and the next. So as we move along, we need to provide some tests for when a series, not a Taylor series, but an infinite series, converges or diverges. So the first test that we look at is the nth term test for divergence. And what this says, now just in passing, generally once we begin talking about infinite series, we sometimes even leave off n equals 1 or n equals 0 to infinity. And it's just understood that when we're talking about infinite series, that we don't have to worry about the indices. So this infinite series will diverge if the limit as n approaches infinity of a sub n is not equal to 0. So what that tells us is that if the terms that we're looking at go to anything except 0, then this series will diverge. It's really important to notice that it's very possible that the limit as n approaches infinity of a sub n will equal 0. That does not mean that the series will converge, and we'll see examples of that to come. The next test that we'll look at is what's called the direct comparison test. And we begin with assuming that a sub n is just any series, and the terms are greater than or equal to 0. First part of this test tells us that this series a sub n will converge if we can find another series which we know converges, and such that after some point all of the a sub n terms are less than or equal to the c sub n terms. All right, so that's a way to show that a series converges by comparing it with another convergent series. In each case, the terms of both series are greater than or equal to 0. Most students will say, how do I know whether a series converges or diverges, and how do I know what series I should compare it with? It's a great question, and the only answer is practice, practice, practice. And similarly, we can use the comparison test to show that a series diverges. And a series will diverge if we can find a divergent series, all these terms are greater than or equal to 0, such that a sub n is greater than or equal to d sub n for some cutoff point. In other words, for all values after some cutoff point. So both of those statements should be pretty easy to believe, and as I said before, the big problem in using the direct comparison test is, number one, deciding whether a particular series converges or diverges, and then number two, trying to figure out the appropriate convergent or divergent series to compare it to. So moving along, we want to define what we mean by absolute convergence. And what we look at is the series of absolute value of terms. So clearly here we allow these terms to be positive or negative. And what we say is that if this series converges, then we say that the original series converges absolutely. And we follow that up immediately with a theorem. So if we're told that a series converges, the absolute value of a series converges, in other words, that this converges absolutely, then what must be true is that the original series itself must converge. We come now to the ratio test for possible convergence or divergence of a series. And so we begin with talking about any infinite series in which the terms are all greater than or equal to 0. And we look at this limit. And if that limit converges to a number L, then we have three possibilities. If L is greater than 1, then the series we're looking at converges. If L is greater than 1, then this series will diverge. And the most interesting one is if L equals 1, there's no conclusion that we can make. The series may converge or it may diverge, and we have to use some other test to determine that. So this is a very, very powerful test, and one that's usually fairly easy to apply. The problem is, of course, what happens if we get L equal 1? We got to move on and try something else. So finally, we have all the tools that we need to answer one of the most important questions around Taylor series, which is, what are the values of x for a Taylor series which give convergence? And for right now, what we're going to be looking at is finding the radius of convergence. And the only difference there is we're not going to be too sure what happens at the end points. But this is close enough, and in the next section we'll learn how to tighten this up completely. So just as with the ratio test, what we look at is the limit as n approaches infinity of the n plus first term of a Taylor series divided by the nth term, and now we want this to be less than 1. And the whole point here is now asking the question, what are the values of x which make that limit be less than 1? So that is how we find the radius of convergence. We look at the limit of the n plus first term over the nth term of a Taylor series, and essentially we find the values of x which force that limit to be less than 1 and hence give convergence of the Taylor series. It should be noted, essentially due to the presence of the absolute value, that the values of x that we find, which force this limit to be less than 1, will actually give us absolute convergence of the Taylor series, and hence convergence itself. It's the endpoints where we may or may not have absolute convergence that we have to test. Okay, so here's an example that we'll look at. Consider this series, pretty weird looking series, and what we want to find is the radius of convergence. So we begin by saying, what's the limit as n approaches infinity of the n plus first term, n plus 1 times x to the n plus 1 over 10 to the n plus 1 all over the nth term, which is n times x to the n over 10 to the n. And what we do is we want that to be less than 1. And again, I think it's really helpful to always write this. We want the values of x, which make that be less than 1. Well, this simplifies to the limit as n approaches infinity of n plus 1 over n times x times 1/10. We want that to be less than 1, and I'll try to keep writing it, and I might forget. Okay, And so now we'll do a lot of simplification, and we'll rewrite this as follows. So we can take out the absolute value of x over 10 because they don't depend upon n, and we're left with the limit as n approaches infinity of n plus 1 over n. And you should be pretty confident to know that that limit is equal to 1. And we're asking for the values of x that make this whole limit less than 1. And so what that implies then is that the absolute value of x over 10 has to be less than 1, which means the absolute value of x is less than 10, which means 10 is the radius of convergence. Now, what that means is x will converge as long as x is greater than minus 10 and less than 10. We don't know what happens at minus 10 and 10. I keep repeating that, and it's worth repeating. In next section, we'll learn how to deal with the endpoints. Okay, so here's something that's fairly important to us. We want to now find the radius of convergence for the Maclaurin series for e to the x. And remember, e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial. The kth term is x to the k over k factorial, and so on. Now, what do you think the radius of convergence is for this series? So we have to look at the limit as n goes to infinity of the n plus first term, which is x to the n plus 1 over n plus 1 factorial, divided by the nth term, and I can kind of simplify this, you should be able to figure it out, n factorial over x to the n. That has to be less than 1, and right, we are asking the question, what are the values of x, which make it be less than 1? So I can simplify this a great deal, take out absolute value of x, and I'm looking at the limit as n approaches infinity. Well, don't you know that n factorial over n plus 1 factorial is just 1 over n plus 1? And we want this to be less than 1, and we're looking for the values of x which make it be less than 1. Well, you're all very bright, boys and girls, men and women, and that limit, you know, is 0. And so therefore what we have is the absolute value of x is times 0 is less than 1. Well, what values of x will that be true for? All values of x. In other words, this series will converge to e to the x for all real values of x. Pretty impressive. Be worth it for you to try to do the same work with the Maclaurin series for sine x and cos x, and you should be able to discover that each of those converges for all real numbers also. Okay, as one final example, let's go about and find the radius of convergence for the Maclaurin series for ln of 1 plus x. Now, we've seen already that that series is equal to this. So we'll proceed as we have in the past. So here's our statement that we're looking for. We take the n plus first, we divide it by the nth, which means we can simply invert and multiply. That limit has to be less than 1, and we're asking for the values of x which make it be less than 1. Now notice, since we're dealing with absolute value, these minus 1 to the powers basically become insignificant, and we can rewrite this as follows. So by pulling out absolute value of x and looking at what we're left with, we just have the limit as n goes to infinity of n over n plus 1, and we know that limit to be 1. So therefore what we get is the absolute value of x must be less than 1, which means the radius of convergence is 1. So therefore, we know that we get convergence when x is greater than -1 and less than 1. The question is, and it's an important question, and I'll say it for the last time, we'll look at it next section, what happens when we equal -1 and when we equal 1? Okay? See you next time.